Okay, so after the initial background material on alkyl halides, and what we do for each functional group in each of the chapters for organic chemistry during the year is we talk about, first of all, their general structures and any structural features that they have. So remember, for alkanes, we talked about the fact that they're hydrocarbon and nonpolar, a little bit about their boiling points, like the branched or straight chained alkanes had higher or lower boiling points. And after we talk about their physical properties, then we talk about naming. And then we usually talk about how to make that particular um, functional group. So how do we make alkyl halides? Well, that was covered on Friday's reading from the textbook. We use free radical halogenation, which is a review of what we talked about back in chapter 4. So after we talk about how to synthesize or how to prepare that functional group, then we talk about reactions of it. With alkanes, we talked about the two major reactions, which were combustion and free radical halogenation. So for alkyl halides, there's going to be two classifications of reactions that alkyl halides can undergo. The first is going to be called substitution, and the second is going to be called elimination. And it turns out that in substitution, there's two classes of mechanisms that substitution can undergo by. What we call SN2 or SN1. And we're going to talk about each one of these. We'll talk about SN2 in this lecture, and then we'll talk about SN1 on the 1-4 Wednesday. And for elimination, there are two possible mechanisms. One is called E1 mechanism, and the other is called the E2 mechanism. So for substitution, what happens is that if I have a carbon attached to a halogen, it could be iodine, chloride, bromide, or fluoride. We saw on Friday that the delta minus and delta plus charges of that polar covalent bond would make this carbon then electrophilic. So what that means is that a nucleophile could attack or could react with this delta plus charge. We'll see the attack today. So substitution, we take a nucleophile, and this is my generic form of a nucleophile, and I'll get into the specifics of nucleophiles here in a minute. But one thing we know about nucleophiles is they're electron rich. Remember, electrophilics are electron poor, represented by the carbon having a delta plus charge. So nucleophiles have a lone pair, and in this case, we're going to use nucleophiles that have a negative charge. So that negative charge or that lone pairs makes a nucleophile nucleophilic. So what will happen is that we'll do substitution. The nucleophile will replace the halogen in the reaction. So we'll substitute the halogen for the nucleophile in this substitution reaction. Now this substitution reaction can occur by one of two mechanisms, and today we'll talk about the so-called SN2 mechanism. But the electrophile portion then is the carbon attached to the halogen. What kinds of nucleophiles can I use? Well, my nucleophiles can be things like hydroxide. They could be another halogen, so we could use like iodide or chloride or bromide. They can also be things like a cyanide ion, Cn-. It could be a C triple bond C-. There are lots of negatively charged nucleophiles that we can use to do this substitution reaction. And so what I'm going to do is just simply replace the halogen with that nucleophile. And when it's a Cn-, I'm going to end up attaching, the alkyl group's going to end up attaching to the carbon of the Cn group, a CN group is a C triple bond N with actually the carbon having the negative charge. Okay, so that's substitution. We can substitute the halogen for a nucleophile. And I'm going to start with negative nucleophiles. And then for Wednesday, in Wednesday's pre-class lecture, we'll talk a little bit about what makes a good nucleophile versus what makes a poor nucleophile. So what's elimination? Well, in an elimination reaction, what we actually have is we have our carbon attached to the halogen, and then on the carbon attached to the carbon with the halogen, there's a hydrogen. The terminology that we'll use for this, just to introduce this now, is the carbon attached to the halogen is called the alpha carbon, and then the carbon attached to it is called the beta carbon. And the hydrogen attached to the beta carbon is called a beta hydrogen. So what happens in this case is that if I take this alkyl halide, and I can do one of two things. I can either sort of react it with heat. What I'll end up doing is I'll end up losing HX. And I'll end up forming a carbon-carbon double bond. So elimination means that I lose HX. This is often called a dehydrohalogenation, because I'm losing the hydrogen and the halogen. So for dehydrohalogenation, we end up forming an alkene. That's the elimination product. Now this reaction can also occur by taking and reacting this alkyl halide with a base. And the base then will actually deprotonate the beta hydrogen, and then we'll lose the alpha halogen, so that what I end up doing is attaching that hydrogen after the base deprotonates the beta hydrogen. I'll then end up with that. I'll end up with the halide ion, and I'll also then still end up with the carbon-carbon double bond. So this is our basically a base-induced elimination to form the double bond. Now, what kinds of bases am I going to use for this? Well, I'll talk a little bit about this again for Wednesdays, but the base that I'm going to use here is a Bronsted base, which means that it can accept a proton. And our problem with bases is going to be that all this list up here of nucleophiles, all of these are actually bases because they can all accept a proton. So when we do dehydrohalogenation, or when we do base-induced elimination, the kinds of bases that I'm going to talk about are bases that are actually deprotonated alcohols. And if this was ROH, and remember R is an alkyl group, ROH is an alcohol, a deprotonated alcohol is called an alkoxide ion. And so if we take alkoxide ions, they're actually strong enough bases to deprotonate the beta hydrogen and start this process to give us a carbon-carbon double bond. Now your book talks about using different types of bases like OCH3-, which is called methoxide, and OCH2CH3-, which is called ethoxide. Okay, that's the methoxide is the alkoxide of methanol. The ethoxide is the alkoxide of ethanol. The kinds of bases that we'll use for this elimination are going to actually be, the one that we'll use the most is this one. And when we get to this in a few days, this is actually what's called tertiary butoxide, because this is the deprotonated form of tertiary butyl alcohol. So when we get to talking about eliminations with bases, we'll have to talk a little bit about the issue of what base to use. And actually the size of the base will play a role in what type of elimination that we get as well. But what we're going to talk about today is substitution. Okay, so we're going to substitute a halogen for with a nucleophile. So there's some terminology that we have to talk about here in doing a substitution reaction. The first thing that we said before was that the carbon is slightly positive, the halogen is slightly negative, and what that does is that sets up this carbon being electrophilic to then react with the nucleophile. Now, the nucleophile is called the nucleophile. This halogen, though, is also what's called a leaving group, because over here it leaves as an anion. Actually, it leaves as another nucleophile. So the reason that we call these reactions, these class of reactions, nucleophilic substitution is because I'm substituting a nucleophile for a halogen, and in the process I'm actually really substituting one nucleophile for another, and that's why it's called nucleophilic substitution. Okay, so this halogen that is leaving is called the leaving group. So that's a term that we'll use over and over again, the idea of the leaving group. Now, an SN2 mechanism, and as we go through I'll explain what the 2 stands for. The S stands for substitution, and N stands for nucleophilic. So again, this is nucleophilic. I'll explain what the 2 stands for in a few minutes. But the mechanism for nucleophilic substitution, that mechanism can occur 2 ways, and we're going to talk about the first one today. So in an SN2 mechanism, what happens is that the nucleophile takes its pair of electrons and it donates it to this carbon. And this is a nucleophile electrophile reaction. The problem is if your nucleophile is going to donate its pair of electrons to form this nucleophile carbon bond, this carbon's got to lose or break a bond in order to not form 5 bonds, which is still not allowed in our organic class. So what happens is that as the nucleophile comes in and forms the nucleophile carbon bond, the carbon halogen bond breaks, and that pair of electrons moves to the halogen so that it forms a halide ion. Okay, and so what we have is we have nucleophilic substitution, but we have the nucleophile, what I'm going to say, attacking this carbon and then kicking off the leaving group. Okay. Now, we actually know that this is the mechanism by a number of pieces of evidence that I'll go through during the course of talking about SN2 mechanisms. So when we get the nucleophile then attacking the carbon and kicking off the leaving group, it turns out that this mechanism occurs in one step. In other words, the nucleophile attacks the carbon, and while it's forming the nucleophile carbon bond, the carbon halogen bond is breaking. So this is a one-step, or what we sometimes call concerted mechanism. A concerted mechanism means that the bond breaking and the bond making occurs all in one step. Okay. So here's actually how the mechanism occurs with the nucleophile attacking the carbon. It's known from the experimental evidence that I'll show you that the nucleophile actually attacks the carbon down the carbon halogen bond. So the nucleophile comes in and it donates its pair of electrons to the carbon, and then the carbon halogen bond breaks. This is sometimes called backside attack or backside displacement. As the nucleophile comes down from, in essence, behind and kicks off the halogen bond. Now, what happens then is that since this is a one-step mechanism, we have a transition state for that mechanism. So if we go back and remember our transition states from free radical halogenation, remember that the transition state is simply the in-between the reactants and the products of that mechanistic step. Now, this is kind of a strange reaction because since this reaction occurs by one mechanistic step, that mechanistic step then is the rate determining step. And so the overall reaction, just being one step, has that as its mechanistic step. So when the nucleophile comes in and attacks the carbon and the carbon-halogen bond leaves, our transition state would look like this. It's an average between a nucleophile, between no nucleophile carbon bond, and between a nucleophile carbon bond, so we put our dotted line. It's also in between having a carbon-halogen bond and breaking a carbon-halogen bond, so it gets a dotted line. Now, in the free radical halogenation, there were no charges during that reaction, so all we did was, in essence, average the bonds between the reactants and the products. Now, because this reaction involved charged species, we have to average the charges as well. So the nucleophile is going from being -1 to neutral, and so therefore in the transition state, you have a delta minus charge on that nucleophile. The halogen is going from being neutral to -1, so therefore it also has a delta minus charge. And what's known from this mechanism is since the nucleophile attacks the carbon down the CX bond, this transition state is actually trigonal bipyramidal, with the nucleophile and the halogen being kind of what we would call the axial positions of the trigonal bipyramidal geometry, and then the three groups that were attached to the carbon occupy then what we would actually call the equatorial positions of the trigonal bipyramidal geometry. So this is our transition state for an SN2 reaction. Partial nucleophile carbon bond, partial carbon halogen bond, and then partial charges on the nucleophile and the carbon as they go from either being -1 to neutral or neutral to -1. Okay, so again, this transition state and this mechanism comes from a lot of experimental evidence. Here's a picture of that trigonal bipyramidal transition state. The nucleophile and the halogen, 180 degrees away from each other, and then the three groups that are attached to the carbon are going to be at 120 degrees away from each other. Okay, so there's just one transition state for this reaction because it has one mechanistic step. Free radical halogenation had initiation, the two propagation steps, so it had a lot of elementary steps for its mechanism. For SN2, it's one concerted step. Okay. If we were to draw the reaction coordinate diagram for an SN2 reaction, it would look like this. We'd have our reactants and our products, and we would then have our transition state having that structure. We would then, if we wanted to, we would have our activation energy here between the reactants and the transition state energy. So the key thing is for an SN2 reaction, you get one transition state. There are no intermediates in this reaction because there is only one step. So there can't be intermediates when you have a single mechanistic step. Now, what people did was they determined the kinetics of SN2. And this is actually where the 2 comes from. So from general chemistry, if you go back and remember general chemistry, if you were to react molecule A and B, it would go by some rate, and you'd have a rate constant then for that reaction. And so you have to determine the overall rate. Okay, and I'm going to put this in here. you have to determine the overall rate equation. That has to be determined from experiment. So what people did was they doubled the concentration of the nucleophile, held the concentration of the alkyl halide constant, and determined the rate of the reaction. So when I double the concentration of nucleophile, what happens to the reaction? Does it remain the same? Does it double? Does it quadruple? What happens to the rate of the reaction when I double the concentration of nucleophile? What happens to the rate of the reaction when I double the concentration of alkyl halide? So what people found was that for what became known as SN2 reactions, when you doubled the concentration of nucleophile, the rate doubled. Or when you doubled the concentration of alkyl halide, the rate also doubled. So that led to forming this rate equation. So the rate equals the rate constant times the nucleophile to the first power times the alkyl halide to the first power. Okay, and so when you double the rate, double the concentration of nucleophile, you're going to double the rate. If you double the concentration of alkyl halide, you're going to double the rate. If you double the concentration of both, the rate's going to go up 4 times. Now, this exponent is called the order of the reaction. Actually, this is the order of each of the 2 reagents, and then the overall order of the reaction is the sum of the exponents. So what we would say is, we would say that this reaction is first order in nucleophile and first order in alkyl halide. And overall, it's second order in that reaction because 1 plus 1 is 2. That's where the 2 comes from. Now you'd have to go back to general chemistry and remember, what is a second order reaction? What does that mean? Well, in this reaction, we know what the important transitions or what the important mechanistic step is for this reaction because there's only one mechanistic step. And so if we went back and we looked at the mechanism, we could define something called molecularity. And the molecularity is how many molecules react in the rate determining step of the mechanism. Now actually molecularity can be defined for any step in the mechanism, but in this case we have only one step, and therefore only that one step is the rate determining step. So how many molecules react in this elementary step of the mechanism? 2. And so this would be called a molecular reaction because 2 molecules are reacting in this elementary step. Okay, so that's a bimolecular reaction. Well, bimolecular reaction also corresponds to the order. So if you have a rate equation that's second order overall, that means that 2 molecules are reacting together in the rate determining step. So this 2 then stands for bimolecular. So this is called bimolecular nucleophilic substitution because in the rate determining step of the mechanism, 2 molecules, the nucleophile and the alkyl halide, are colliding together to form the final substitution product where you've got the nucleophile attached to the carbon and the halogen group as the leaving group. Okay, so the way that this works mechanistically is people first determined the rate of the reaction, and then they had to propose a mechanism that would give you an overall second order reaction And what they proposed was the simplest mechanism, and that's just having the nucleophile attack the carbon and kick off the halogen, and only one elementary step for that mechanism. And so that's what we know as bimolecular nucleophilic substitution. Okay. So this just kind of sums up that general chemistry, the idea that the two is bimolecular, and the reaction where the rate formation is dependent on the concentration of two reactants. That's what's called the bimolecular reaction. Now, when you do substitution in the bimolecular mechanism, what we find is that we can measure the relative rates of reactions of primary, secondary, tertiary halides. I'm not going to do much with vinylic, and vinylic means that the halogen's attached directly to the double bond, or benzylic halides where the halogen is actually attached to an aromatic functional group. I'm not going to worry about those. I'm going to worry about primary, secondary, and tertiary. And here's what we find. Experimentally, primary alkyl halides react the fastest. They react faster than secondary alkyl halides, and it turns out that tertiary halides do not undergo the SN2 mechanism. And so whatever mechanism we propose has to be consistent with these observations, that the primaries faster than secondaries and tertiary would not undergo bimolecular substitution. And if you're curious to say, well, how would you know that an alkyl halide doesn't undergo bimolecular substitution? One of the way that we know that is that when you actually react a tertiary halide with a nucleophile, if you double the concentration of halide, the rate doubles. But when you double the concentration of nucleophile, it turns out that the rate stays the same. And so when people reacted primary halides with a nucleophile, they got a bimolecular rate equation. When they reacted secondaries, they got a bimolecular or second order rate equation. When they reacted tertiary halides, their rate equation changed, and now they had the rate was equal to the rate constant times the concentration of the alkyl halide to the first power and the concentration of the nucleophile to the 0 power. And you know that anything that's to the 0 power is 1. So what they really saw was that the rate was only dependent upon the concentration of the tertiary halide to the first power. In general, in chemistry, when your rate equation changes, that means that your mechanism changes. And the next lecture will deal with this reaction of tertiary halides and why this rate equation changes and what that means for the mechanism. But just accept the fact that these two guys both followed that the rate was equal to the concentration of halide to the first times nucleophile to the first, but then the tertiary halides changed their rate equation and so therefore didn't undergo SN2. But now let's go back to our mechanism. Is our mechanism consistent? Is this backside attack of nucleophile onto the carbon, onto the electrophilic carbon, consistent with the observation that primaries react faster than secondaries? Well, in order to rationalize that, we have our nucleophile backside attacking this carbon, which I've colored in red. So if you had a tertiary, if you have a primary alkyl halide, you'd have one alkyl group attached to the carbon and two hydrogens. Well, this would be the view of the nucleophile attacking down the carbon-halogen bond, the carbon being in red and the halogen being in green. Well, you can see that with just one alkyl group attached to the carbon, you have the ability, the nucleophile does have the ability to come close enough without any steric interactions to this carbon to form the nucleophile carbon bond, and then move to the transition state and kick off the halogen in the substitution reaction. If we go to a secondary halide, you can see that with two alkyl groups, the backside attack is being somewhat negated by these two methyl groups. But the reality is there's still not enough steric hindrance for the nucleophile to come in and attack that carbon. Okay, but the reaction is slower because now there's steric hindrance from these two methyl groups around that carbon versus there just being one. Okay, for those of you that are really into mechanistic details, here's what's happening. As we go through a primary halide, our primary transition state has a lower energy because the nucleophile can more easily approach the carbon. And so that transition state between where the nucleophile is partially attached to the primary carbon, that transition state is a lot lower in energy than the transition state you would get if you went to the secondary, with it starting with a secondary alkyl halide. So with these two alkyl groups, that transition state energy goes up, and of course your activation energy goes up, which means going through the secondary alkyl halide transition state occurs slower than going through the primary one. But if you look at it just in terms of steric bulk, secondary is more bulky than primaries, therefore the nucleophile is going to have a harder time reacting with that carbon. Now, it is possible for some secondaries to not undergo SN2. Like if I put a tertiary butyl group here around this carbon that's got a methyl and a hydrogen, so technically this carbon is secondary. But if this big tertiary butyl group's thrown in, you can actually see that the nucleophile is going to have a very difficult time getting to that carbon. And so what happens is that the addition of the tertiary butyl group raises that transition state energy even higher. And at some point, that transition state energy and that activation energy becomes so high that the mechanism is the molecule will not be able to undergo SN2. And it'll find another mechanism to undergo. When we go to a tertiary halide, the three alkyl groups pretty much completely block the carbon, and so therefore the nucleophile cannot attack that carbon from the backside. And so a tertiary halide is prevented from undergoing backside attack and therefore has to go through another mechanism in order to do substitution. So this backside attack mechanism is consistent with the observations that the primary, secondary react with an SN2 mechanism, but primaries react faster than secondaries, which is our observation. And since the steric bulk around the carbon with the tertiary halide is so high, that nucleophile will not undergo SN2, so tertiaries won't. So those observations then are consistent with this backside attack mechanism. Okay. So the final sort of piece of evidence that people used to prove that this backside attack or backside displacement was the mechanism for SN2 is they used a chiral molecule. And so if you think about what happens in this reaction, if the SN2 mechanism is actually backside attack, that means that if I took, for instance, R2-bromobutane, and I purified and I had only the R enantiomer, that when the hydroxide comes in and attacks this carbon and kicks off the halogen, and it goes through this transition state, the OH would be on this side of the molecule after kicking out the bromine. And so if we started over here, we would say this would be priority group 4, priority group 1, 2, and 3. So this is the R configuration, whereas over here in the final product, we would get priority group 1, priority group 4, 2, and 3. We would get the chiral carbon then inverting, and this is the term we use, inverting its configuration, so that if we started with the R alkyl halide, we would get the S product. If we started with the S alkyl halide, we would get the R product. So this is actually what's observed. People did many of these SN2 reactions with optically active alkyl halides, and what they saw was they saw that this mechanism actually caused the product to be optically active. So it wasn't just a random attack of the hydroxide to this side of the carbon or this side of the carbon, because if that was the case, we would get a racemic mixture with zero optical rotation, which we'll actually see on Wednesday from another mechanism. But they saw inversion of configuration from R to S and from S to R. So this was sort of the final piece of information that proved that SN2 was a backside attack of that alkyl halide. Now you might say, well, isn't front side attack possible? And the answer would be no, not if the evidence shows that it's backside attack. But think about what would happen if we had quote unquote front side attack. If you had front side attack, that means your hydroxide would come in and kick the halogen off this way, so that what you would end up with is retention of configuration. And so if you started with S, you would get S. And so that if front side, we'd say if front side attack occurs, then what you would end up with is retention. And all we observe is inversion. And so what that means is, that means that it has to be backside attack, no front side attack. Okay, so front side attack doesn't occur, so we can just cross out front side attack. The experimental evidence is that we always get inversion of configuration when we undergo SN2 substitution. Okay. Now, later on, after the chirality experiments had been done, people found out the orbital reason why SN2 occurs by backside displacement, and that has to do with sort of the orbital picture of our organohalogen, or of our alkyl halide. And so if we looked at a picture of, let's say, well, I'll just make this a primary halide. So this carbon then is tetrahedral. It's got sp3 hybridization. The bromine actually has sp3 hybridization as well, because it's got its lone pairs in sp3 hybridized orbitals. But here's where I'm going to go back to when we talked about hybridization, the idea that the lobe here, the sp3 hybrid orbital lobe, has this little tiny guy in the back that we rarely talk about. But we're going to talk about it. Because what happens is that when the nucleophile comes in, and let's say if this nucleophile was a hydroxide ion, that hydroxide ion would be sp3 hybridized. So when the nucleophile comes in with its hybrid orbital that has the lone pair of electrons that it's going to use to form the nucleophile carbon bond, what happens is that from the orbital picture, remember that we form carbon, or we form single bonds by the head-to-head overlap of orbitals. And so what happens is that this nucleophile then comes in and overlaps its sp3 orbital with the little tiny sp3 orbital that we never worry about. And so then what happens is this carbon atom flattens out in the transition state to form then the trigonal bipyramidal geometry. And then after the nucleophile, after the halogen leaves, you're going to end up with a little tiny lobe reforming on the other side of the carbon. So the orbital picture of this says that if you have to head-to-head directly overlap one orbital with another orbital to form a bond, a single bond, then the only orbital that's available that's empty for this lone pair to be donated into is the little tiny sp3 hybrid orbital that we always forget about, that's opposite the sp3 hybrid orbital that's bonding the bromine. And so the reaction has to go inversion of configuration if we know that that's how reactions occur, by the bonding of orbitals and by the overlap of orbitals. So all this information then comes together to form what we know to be SN2 substitution. So what do we know about SN2 substitution? We know that the mechanism is a backside attack of the nucleophile to form a trigonal bipyramidal transition state, and then the halide ion leaves. We also know that SN2 reaction is bimolecular in kinetics, and so the kinetic rate of forming the substitution product depends on the concentrations of the alkyl halide and the nucleophile, each to the first power. So it's first order in halide, first order in nucleophile, and overall second order, therefore bimolecular. And due to the backside displacement of the nucleophile, the alkyl halides, the relative reactivities of alkyl halides is determined by the number of alkyl groups that are attached to the electrophilic carbon. Primaries react fastest, secondaries react a little bit slower, but tertiary and the other reactions, and in particular tertiary, does not undergo SN2 reaction because there's too much steric bulk there. And then because of the backside displacement, an SN2 reaction of an optically active chiral halide does result in an optically active product, and the configuration of the chiral carbon is inverted, going from the halide to the final product. So if you started with R, you'll end with S, or vice versa. Okay, so these are the basic facts for bimolecular substitution, SN2. And so what we'll talk about and do problems with in class are further writing of mechanisms and looking at some of these experimental details on how we can do SN2. Now you may say, but if tertiaries don't undergo SN2, does that mean that they can't undergo substitution? And the answer is no. They will undergo, tertiaries will undergo substitution, but not by the SN2 mechanism. Okay? So that's what we will talk about on Monday, October 22nd.